In the name of God, the compassion of the merciful, hello ladies and gentlemen, fellow speakers and dear audience joining us online in the 12th International Conference on Computer and Knowledge Engineering held by Ferdowsi University of Mashhad. I'm Salimi-Badr, here to present our paper titled An Efficient Planning Method for Autonomous Navigation of Wheeled Robots Based on Deep Reinforcement Learning, co-authored with Dr. Armin Salimi-Badr, Dr. Malek, and Mr. Mahdi Shahbazi Khojasteh, all from Faculty of Computer Science and Engineering at Shahbazi University. According to our table of contents, in the introduction part, firstly, I'm going to talk about problem definition and then the factors to be seen and the proposed solution. Secondly, I'm going to talk about the other approaches and the other perspective to look at this problem and the other proposed solutions. And moreover, I'm going to introduce our proposed solution, our methodology, experiments, and at last, our conclusion. In the introduction part, I'm going to talk about the problem definition. Autonomous navigation is a problem that consists of two factors, two matters, path planning and obstacle avoidance. Path planning is actually the process of finding the best plan, the best path for going from point 1 to point B, and the obstacle avoidance in the process of modulating the trajectory based on the real-time sensor readings to avoid collision. Avoiding collision and obstacle avoidance is the most important factor in this navigation part, because it's obvious that not avoiding collisions can actually lead to not getting to the destination that has been predefined for us. Now we know the problem. The problem is autonomous navigation, going from point A to point B with the best path planned and also avoiding the collisions. So, talking about path planning and autonomous navigation, the best plan and also the best and efficient planning is the one that considers the best energy, the least energy cost, the smooth routing, the shortest path distance, and also minimal locking time. These factors are the most important things that need to be optimized. One solution can optimize one of them, one can optimize two, or the best solutions can propose methods and solutions to address all of these factors and gives the best solution. So, after knowing the problem and the factors to be seen in the solution, the proposed solution, I'm going to talk about the other approaches, the approaches that have been proposed during the time. APF, or artificial potential field, behavior decomposition, graph search methods, and also genetic algorithms are the ones that have been proposed during the time that the autonomous navigation problem has been introduced. APF, or artificial potential field, models the target as an attractive force and also the obstacles as repulsive forces, and the contradiction of these two forces make the resultant force that moves the robot toward the target point. Behavior decomposition, it's actually a great way for breaking down the wayfinding problem. It breaks down the problem into tracking, collision avoidance, and target guidance. It has some downfalls and disadvantages I'm going to talk about in the next slide. Graph search methods are the one that uses predefined maps. It's actually a map-based solution. That's the well-known one of these algorithms is the star algorithm. It's actually the most famous one, kind of. And genetic algorithm that it's actually can start the solution, giving the solution with no prior knowledge, and with actually a good probability, we can say that it gives the best solution, the right solution, and also it has some downfalls I'm going to talk about. Talking about the disadvantages, APF is map-based. The solution we're going to talk now. So the map-less autonomous navigation is a problem we're going to target in here. So using map beforehand is a disadvantage that we can consider in APF. We can get trapped in the local optima, and it can fail to reach the target point where the repulsion force is higher. Behavior and decomposition, it actually does not need any prior knowledge, but the final path is not very optimal. It's not the optimal trajectory. Graph search method, it also needs a map. It's a map-based method, and the model should describe the environment and very abstract. Actually, it's not so realistic. We need more realistic solution in these real-world kind of problem. We need to address real-world problems, and actually B star and graph search methods are problems that need a discrete map-based solution that are not really for industrial or real-world problems. And genetic algorithms, it can get trapped in the local optima, but as if not, the searching and optimization of these approaches is very slow and in real time. So after knowing the knowledge of the problem or solution and the other solution that has been introduced, we're going to talk about the methodology of the proposed method. So deep reinforcement learning, or DRL, is a combination of DNN, deep neural networks, and reinforcement learning. Talking about the reinforcement learning, here using RL algorithms that are based on punishment and rewarding can give us a good performance in complex environments. Parameter tuning through interaction with the environment. It actually got an agent, an environment that can have an interaction with, and tuning these parameters is more realistic. It definitely can have better navigation through simpler search. Application in high dimension or high state space can be addressed using DRL, and it's model free. It can be model free and low dependence on the map. So for unknown environments, DRL can be used if the policy is well defined, well trained, and the reward function is well defined. We can be assured that in unknown environments, DRL can work well. And after knowing these works for DRL, we can now propose and talk about one of these algorithms that are used nowadays. It calls DDPG, Deep Deterministic Policy Gradient, is the DRL algorithm that we use to solve this problem. Since actions are continuous, angular velocity of wheels, we use DDPG for our RL architecture. It's based on off-policy actor-critic network. It's an actor-critic based network where we're going to see the network architecture in the next slide. It uses experience replay, of course, and target network to solve the continuous action problem, and strong fitting ability is one of the perks that DDPG has, and it can generalize well as optimal action learning. So in here we can see DDPG actor-critic network model. In the actor section, we can see it gets the current state as an output, and the output is a real value indicating an action. And the output of the critic network is the estimated key value of the current state and the action given by the actor. It has a connection with an experience pool, and it has an interaction with simulation environment with action on the state. And our simulation environment is VWATS, we're going to talk about in the experiment section. So we have designed a reward function with three steps and with three models. The first model just uses a target distance reward. It's a Euclidean distance between our target and our robots in each step of the robot. The second model uses target distance reward, also obstacle avoidance punishment. The obstacle avoidance punishment is calculated using the maximum value of the 8 rangefinder sensors of the robot, and we predefined a threshold for the obstacle avoidance punishment. If the RF value, the maximum RF value, is bigger than the threshold we predefined, we can say that the obstacle is near the robot, and we need to punish the agent dynamically. And for the third model, we have used the combination of the first two and also the heading angle reward. We really compute in each step the angle between the heading of the robot and also the target, and if the angle increases, the punishment increases dynamically too. And the third model is a combination of these three, and in the conclusion results we can see the effect of these three models on the final result. So we have talked about the three-layer design of a reward function, and we've used actually gradual learning for this matter, and we use the saved weights with a simple environment, and we trained using a simple environment, and we saved the weights of the simple environment, for example, without any obstacle in it, just getting to the target point. After that, for the second, more complex environment, we load the saved weights of the previous environment, and we kind of fine-tune the previous weights. And with this method, gradual learning, we can achieve more and more complex tasks and more complex environments. And we use this kind of method for trainings, and we use AT training environments with gradual learning. So, talking about our experiments, we have used WeBot's simulation environment, and we used Epoch as the mobile robot, which consists of 8 infrared sensors measuring ambient light and proximity of obstacles in 4 centimeter range. And together, data set for training, we created our environments by ourselves. And navigation task is a task that we didn't use any prior knowledge, and our environment is given in the test environments. So the architecture of our networks, the actor network is portrayed in orange, and the critic network is in blue. So in the orange, and the actor network, we can see we used fully connected for this first layer, and the liquid layer for the activation function, and we use batch memorization layer for each layer to ensure the stability of the algorithm. And the structure of the critic network, that is in blue in here, is the same, but only a slight distinction is the last layer, where after the FC layer, fully connected layer, comes the ReLU, and the activation function with no batch normalization, just for the last layer. So the parameters and hyperparameters use learning rate and batch size we stated here. The weight of both network is initialized using Xavier uniform initialization, and the optimizer of the actor is Atom, and the critic network is ARMS prop. So we talked about the environments, the test environment and training environments that we I told you beforehand is like these pictures in this slide. On the left side, we can see some of the training environments. And we can see in the first steps of the gradual learning, we have used really simple environments. The ROI AA lab of Shahbazi University logo is on the left, and the robot is on the right. Is a slight kind of way between a robot and target, and we have a really small obstacle, and gradually we can see it gets more complex. And on the test environments, we have 2 environments. That for the environment 1, we have no obstacles, and for the environment 2, we have multiple obstacles. That it's kind of challenging task for the robot to solve. So for the results, on the first record of the table, we can see reference results of the proposed method of Mr. Shahbazi and Mr. Khojasteh, and for example, the results of these methods and the implemented method, we actually use this implemented method of this reference on our 2 test environments, and the results are here. For their proposed method, it has converged in 180 episodes. It has actually solved the problem, just finding the path between origin and destination of the robot, and the arrival time in seconds is 5.46. Our proposed method in Model 1 and Model 2, we use target distance with obstacle avoidance, and target distance with heading rotation. Also, obstacle avoidance, we can see the time that it has solved the problem is 33 and 9. And the best case is for the first model, we can see it solves with 5.01, and with 9 episodes, it can solve the problem in the test environment 1. For the test environment 2, the referenced method does not solve the problem. Actually, it's kind of obvious because it does not contain obstacle avoidance, and we can see that it cannot solve the problem. We just used one of the reward function that has been proposed in the reference, and for our second and third model, we can see that we have solved the environment using 56 and 13 episodes. Now the arrival time was 4.83 for our best case scenario, and we can see that combination of these 3 factors that we have introduced in the reward design slide, that the combination can be really good, and the results can show that. In our conclusion, we can say in this paper we propose a planning method based on DRL. It's presented to navigate a differential drive robots avoiding collision. We have designed a reward function with a 3-layer design system. It was a proper reward function designed with considering 3 factors: distance from the target, obstacle avoidance, and also orientation from the robot. The approach actually we use is consists of using DDPG architecture, designing reward function, and also we used gradual learning for better convergence. And for the final notes and future work, we can say the proposed method can be improved using adding new camera and the new sensory input, and we can use the visual data to form a visual navigation method. We can use more complex and more realistic environment like AI to Thor simulation environments, and it can address our problem with more real-world problem, and it really improves this navigation problem solutions. Thanks a lot. Thank you for your attention. I hope this has been informative and helpful.